Welcome to this video dealing with functions and inverses, graphical and algebraic. It's effectively a recap and most suited for those doing Maths Methods 3 and 4, although it may apply to other students covering A-levels or similar courses. As I say at the start of every video, this is basically based on the Cambridge Essential Mathematics textbook 3 and 4, and no intention has been made to infringe copyright. It's just an excellent resource. So if you are out there following these videos and could get hold of a copy of the book, I would seriously recommend it. Absolutely outstanding. So let's recap what a function is defined as. And according to the textbook, it says it's a relation that no two ordered pairs of the relation have the same first element. Now, an ordered pair is effectively a coordinate, and what's that saying in layman's speak is that, well, if there is one x value, there is only one y value, all right? So there is no repeat. They don't have simultaneous values. And as an example, if you look at the two graphs here, if we were to draw a vertical line through an x coordinate, then what we find is that here, because it crosses twice, there are two y values. So this is not a function, right? It is not defined as a function. And as hopefully you're aware, that would be an x squared plus y squared equals r squared relationship. So circles don't fit. However, this, which probably would be some form of y equals x squared, is a function. Why? Because again, if we draw a vertical line through it, we notice that it only crosses at one point, and as such, when there is one x value, there is only one y value. All right? So that's the definition of a function. There are sub-definitions, I suppose, and one of the definitions, or one of the sub-functions, is a one-to-one function and a many-to-one function. And how are they defined? Well, this time you draw a horizontal line. And if you notice here, this horizontal line is cutting through my graph y equals x squared, and that's defined as a many-to-one. All right, so that's a many-to-one function. And this here, horizontal line through, what do we notice? It's only crossing through once, and this is a one-to-one function. Now, these are actually going to be quite important to us because one-to-one functions actually relate to the rest of this video with regard to inverses. And hopefully you're aware here that if we have the line function of x equals 5, or otherwise known as y equals 5, there is no way this can be a one-to-one function because, again, it's crossing infinite number of times. So I suppose this would be defined as a many-to-one. But, the general idea of horizontal lines and vertical lines help you define what a function is, and more importantly, whether it's a one-to-one function. Now, if we do have a one-to-one function, and it's defined as, each number y in the range of f, there is exactly one number x in the domain of f, such that f of x equals y. Again, if it is a one-to-one function, an example shown before, then it will have an inverse, right? So that's quite important. There will be an inverse. So, as a quick example, if we look at y is equal to 2x plus 3, and we were to draw a quick sketch, all right, what would we notice? Well, we would notice it would have an intercept of 3, and it would have a positive gradient. So we're looking at something like this. That's a value of 3. Is this a one-to-one function? Absolutely it is, all right, because when we do a horizontal, and in fact a vertical test, we find out it is a function. If we do a horizontal line, we find it is a one-to-one function. So this will have an inverse. But what is an inverse? Algebraically, you're taught that, if it is an inverse, then what you effectively do is where you see a y, you put an x, and where you put an x, you put a y, and you move things around for a short while, and yay! So for example, algebraically, if I gave you function of x was equal to, as I just said, 2x minus 3, what would we do? Well, we think y is equal to 2x minus 3, and what we've been told to do is where I see a y, put an x, and where I see an x, put a y, and rearrange it so that you get y equals again. So the minus 3 moves over to become x plus 3 is equal to 2y, which gives you y is equal to x plus 3 all over 2. And you're generally told to then restate it so that you've got the function of x is given by 2x minus 3, and you have f to the minus 1 of x, which is generally denoted as the inverse, is given by x plus 3 over 2. But although you're doing this algebraically, what does it actually mean? Well, hopefully you're aware that the line of y equals x, if I could draw another really quick and undoubtedly bad graph, the line y equals x is a diagonal line through there. And when you're finding the inverse, what you're really doing is you're reflecting any function in that line, right? So yeah, you're reflecting any graph. So if I had some sort of a function that did that, and I was finding its inverse, generally speaking, what I will get is something like that, right? Now, again, I'm limited with what I can actually draw on here, but the general idea is shown. It's incredibly important to realize that you're reflecting in this line y equals x. Well, how does that help us algebraically? Let's see. If I now look at the idea of our line that is dotted, and I was looking at some sort of function of this, then yep, what I'll do is I'd end up with this now crossing at 3 here, and looking something similar to this. Now, they're not going to be parallel. Again, this is incredibly bad drawing, and this isn't about spending hours drawing diagrams and getting it to look beautiful, but the general idea is it would be a reflection. One of the great things to notice is that this value here on the y-axis became equal to this value on the x-axis, and that seems to suggest something about domains and range, right? Undoubtedly, at this level, you are forever being asked to do the domain and range, or find the domain and range of various functions. And so let's look at this particular example here. Now, strangely, the domain is equal to real values and the range is equal to real values. No big deal. But what we'll later on find out, and perhaps one of the key learning points here is that if you have a function of x where you have the domain and the range, then what you find out is that when you have the inverse, the domain of the inverse is equal to the range of the function. And the range of the function, the range of the inverse is equal to the domain of the original function. Now that's actually incredibly important to us as well, because if they give us an original function and we find out the domain and range, I don't necessarily have to draw this thing to work out the domain and range of my inverse, because the domain and range just inverse. Remember again, you are reflecting in the line y equals x. Now sadly, not all functions will have an inverse function, and I suppose this now comes down to a question of almost semantics. What does that mean? Well, it means if you read what's on the line now, or on the graph now, the inverse of any relation may be defined. Any relation may be defined. The inverse relation is not a function, however, unless the initial relation is a one-to-one function. That's a lot of words for a general concept. Well, let's look at this example down here where we have the graph of 4x plus 1 squared. How is that going to look? Well, roughly speaking, x plus 1, well, it's a quadratic because it's an x plus 1 squared. That plus 1 moves it 1 to the left. 4 is a dilation, and roughly speaking it's going to look something similar to this, right, where this thing is going to cross at -1. Is this a one-to-one function? No. How do we know it's not a one-to-one function? Because if I was to draw a dotted line through it, it crosses twice. It's not a one-to-one function, that's no good. But it is still a relation, right? It is still a relation. And actually, this can have an inverse. Why? Well, there's no reason why, if I draw a line of y equals x squared on here, this can't now have its inverse. And I'm pretty sure you would all be aware that that -1 there would become -1 there. And so my graph is now going to look something like this, right? Actually, that's not bad if I do say myself. So this relation will have an inverse. And if I wanted to, I could go off and do all the algebra I needed to do to work out f to the -1 of x. That's not the scope of this video at the moment. But what I want to say is, how would you turn a relation into a one-to-one function? Well, this is where I suppose you start talking about limiting domains, right? Now, domain, if you remember, is the idea of what values are possible horizontally, or x values are possible. Let's imagine this graph here, the graph of 4x plus 1 squared, but I only look at x values that are greater than or equal to -1. How does that now make my graph look? Well, if I now only look at it where the values of x are greater than or equal to -1, that now means that my graph looks nothing like that, but anyway, looks similar to just this side of the graph. Can that now be reflected in the line y equals x? Absolutely. What is that now going to look like? It's going to look like something like that. Is there now only one x value equating to only one y value? I think so. I'm pretty confident that that is exactly what it is. So if I now restrict my domain, then I can start thinking of this now being a one-to-one function. Again, that's just something interesting to think about. Let's see what we can do when we look at things, algebraically. Let's look at this example with, h of x is equals to x squared plus 2. I'm going to ignore the limit at the moment and just make sure we're all aware of how we're going to draw that graph. Well, x squared is a quadratic, move it up to, it's going to look something along those lines, crossing through 2. I now automatically know that this isn't one-to-one, and hence I imagine that's why they're looking at limiting to my domain. So, right, another quick sketch. What's that going to look like? It's going to look something like this. What is my inverse going to look like? Well, if I now do my dotted line and I do this, wow, that looks pretty cool to me. All right. This should now be a one-to-one function, because if I do my line across, is it going to cross through? Well, theoretically speaking, no, it won't. Again, my diagram isn't fabulous. But what happens if we were to look at this algebraically? Well, let's look at the maths behind it. We've got x squared plus 2 is equal to y. That's my original function of x. Right, so what do I do for my inverse? Well, my inverse is given by x is equal to y squared plus 2. So x minus 2 is equal to y squared. And so y is equal to plus or minus the square root of x minus 2. Well, I know what the graph of root x looks like, right? We've done that previously. It looks something along those lines. X minus 2 is going to move my graph over 2 positions, so it'll start at 2. And what about this plus or minus? Well, plus generally means it's above the axis, and if you remember, this minus in front of the function generally means that it would be below the axis. Well, actually, look at this. I already know that's going to cross at 2. I know that's going to cross at 2. So we would now know that the inverse of this function would be given by y is equal just root of x minus 2, with the limit of x is greater than 0. And yep, I'm pretty happy that the algebra works. One of the main questions you tend to find in our methods 3 and 4 exam may well be asking where the original function and the inverse cross. Now that's interesting, a lot of algebra in there. So let's do this the hard way before I show you the trick. Right, let's have an equation. Well, let's go back to our y is equal to 2x minus 3. Right? So we now know our function of x is given by 2x minus 3. F to the minus 1 of x, how do we find that? Well, we now have x is equal to 2y minus 3. X plus 3 is 2y. Or y is equal to x plus 3 over 2. Right, so I now have my two equations. And we know from previous experience that if we want to find out where they intersect, what do we know? Well, we know that the y values must be the same. So then I equate, and I get 2x minus 3 is equal to x plus 3 over 2. We'll move the divide by 2 up to give me 4x minus 6 is equal to x plus 3. And that will give us 3x is equal to 9. or x is equal to 3. And I would then go off and I'd find out what my y values were. And for completeness, that would be 3. So we now know that these would intersect at 3, 3. This is a pretty trivial example and quite easy, but they do get a lot harder. Is there a quicker way of doing this? Is there a shortcut? Well, actually, it turns out there is. Let's go back to what we were talking about a moment ago with a very quick graph where we have, for example, our line y equals x. So imagine we have our original function does something like this, and our inverse does something like this. So they're going to cross. I have to say, my diagrams are shocking. But let's assume they cross at this point here, which is what we're trying to find. Well, at this point here, what do I actually know? Well, at that point there, it is crossing at the line y equals x. All right? So at the point they cross, the y value is equal to the x value, and the x value is equal to the y value. Well, hold on a moment. I've got two equations already that start y equals. I've got y equals 2x minus 3, and I've got y equals x plus 3 over 2. Well, at this one point where they cross, at their inverses where they meet, well, if I know that y is equal to x at exactly the same point they cross, well, that now becomes a trivial example. So I can let x equals 2x minus 3, or I can let x equals x plus 3 over 2. I can equate either my original equation or my inverse to just x. Well, that doesn't seem sensible. Let's just work it through. Well, actually, it does, because if I equate this here, I get x equals 3, which was the value I was expecting. And if I look at this one here, I get 2x equals x plus 3, or x equals 3. Don't know about you, seems a lot easier than what we did previously. Right? Again, remember, this is a trivial example. Right? The maths fell out pretty quickly. Imagine things with squared square roots, it could get quite nasty. So maybe, again, one of the key learning areas here is the idea that if you are going to try and find where the original function and the inverse cross, just put the original function equal to x, or even the inverse equal to x, solve, and off you go. And please, ladies and gentlemen, realize that if you're finding where they cross, you're looking for a coordinate, and so you will then look, once you've got the x value, to put it back in and get your y value. There's nothing worse than marking exam papers finding people have only ever found the x value. So, almost at the end. One last thing for this particular learning section is this. You may well be asked to find the function of the inverse of the function. Right? So it's one of those interesting throwaway questions. What does it actually mean? Well, let's actually do some examples. I'll use my trivial example again. You've got the function of x is equal to 2x minus 3, and we now know the inverse of that function is given by x plus 3 over 2. So let's do the function of the inverse function of x and see what happens. Now remember, what that means is put the inverse function into the original function wherever you see x. So that will now give me 2, and in brackets, x plus 3 over 2 minus 3. Well, hopefully you'll be happy knowing that the divide by 2 will cancel with the plus 2, the multiply by 2 there. That gives me x plus 3 minus 3, which just gives me x. So the inverse of the function, or the function of the inverse, well, hold on, what happens if I do that differently? What happens if I do it the other way around? What if I want, the inverse function of function? All right? Well, that just means put the original function into the inverse. The original function into the inverse. All right, well, so where there was an x, I'm going to put 2x minus 3. I'll even put it in brackets. I'm going to add 3, and I'm going to divide it by 2. So that gives me 2x minus 3 plus 3 over 2. And that is definitely a minus sign, by the way. Minus 3 plus 3 cancelled. 2 divides into the 2, and once again, we get x. So a little bit of a trick question, perhaps, and I'm sure you can now relate that to what we were doing a moment ago. Anyway, this was a not so quick gallop through functions and inverses. Hopefully this has now cleared up a few problems from the test, and you're slightly more aware of the complexities of functions and inverses.